As someone who greatly admires those who devote their lives to science, it's a pleasure and an honor to introduce you to Dr. David Hastings, Professor of Marine Science, Environmental Studies, and Chemistry at Eckerd College. Dr. Hastings studied chemistry at Princeton University, and he went on to get his PhD in chemical oceanography at the University of Washington. His primary research interest is paleoclimatology, the study of climate change throughout history. Using varying levels of magnesium and strontium in the shells of ancient sea creatures, he can determine past ocean temperature changes, and he uses this information to better understand mechanisms behind climate change, both what they were in the past and what they can be in the future. Dr. Hastings believes that it's important for scientists to actively engage in policy conversations and with the public and with elected officials. He frequently participates in these conversations, most recently meeting with Florida Governor Rick Scott to discuss both the science of climate change and the imperative of taking immediate action in Florida. Dr. Hastings focuses on solutions while also articulating the scientific basis for the tremendous concerns scientists have for the future of our planet. And he seeks to correct any misinformation that could illy affect the decisions our political representatives could make. He was selected as 2014 Scott Science Champion by the Union of Concerned Scientists for his public outreach and his informing about the reality and potential ramifications of climate change, should it go unaddressed. And his life's work helps prepare us for any and prevents any further consequences of our past indifference. So everyone, please join me in a warm welcome for Dr. David Hastings.
Hi there. What a pleasure. Hi, I've never been to Shorecrest. I lived here for 20 years. So thank you very much for inviting me. And so I study ancient, old temperatures of the planet, various places. And in doing so, I've become very engaged in what the temperature of the planet might be in the future. And because that turns out to be a really interesting policy conversation with politicians, I've become involved in some of that aspect as well. But fundamentally, I'm a scientist, and I really care about data, and I really care about numbers, and I care a lot about what's true and what's not true. And 20 years ago, I didn't think that was really up for conversation, but seeing what's happened around the conversations about climate change, it turns out that that is in fact very important. We're going to talk a little bit about climate change, and we're going to talk a little bit about kind of real or fake, whether the numbers, what these numbers mean. I'm at University of Florida this year. Normally I'm at Eckerd College here. I'm at University of Florida, and they care a lot about football. I don't think actually you care that much about football, but that's fine. Okay, so climate change. It's a big room here, so I'm not going to ask you to call it out. But what are two things you know about climate change? Just think about it for a moment. Two things you know about climate change. Two. How do you know those things? How do you know them? Think to yourself, how do you know them? Why do you know them? What are your sources of information? Where did you get that? Did you get it off the web? Did you get it from bowling with somebody? How did you get that information? Yeah, you have a good bowling team too, right? Congratulations. I am horrible at bowling, so we're not going to go there. The main thing I want you to think of is, how would you change your mind about what you think you know given new information? So if somebody told you that my shirt was red, would you be willing to change your mind? Yes. Probably. Well, some people yes, but most of us no. Most of us are very reluctant to change our mind about something we think we know. So this concept of what we know and how we know it is very interesting, especially to somebody like me who looks at data, numbers, figures. You know exactly how old you are, and if somebody told you you were 19, you probably would disagree with them vehemently because you know how old you are, and I know data about climate change. So two things you know about climate change, and then one thing that you're uncertain or confused about. What's not quite certain there? And why aren't you certain about it? What is it that makes you uncertain? What is it that drives that? And what would convince you, what would resolve that uncertainty? These are interesting questions, and I'm not going to answer them now, but I want to back up for a minute and say that scientists are very comfortable with uncertainty. In fact, that is part of our business, is knowing what we know and knowing what we're uncertain about. And yet, in the policy realm, we are very uncomfortable with uncertainty. And that's part of the challenge of what we've got going on. This is a little factoid I found on the web, and it just helps us understand what we're talking about here. Over 30,000 scientists said that this global warming is a complete hoax and science lie. 30,000 scientists. There is an aspect of this that's true. So, in fact, there was a petition, and notice the date is relatively recent. There's a petition that was circulated in 1998. That's a long time ago. You'd think if this were important, they'd find a more recent study. 1998, and anybody could sign the petition, and anybody did sign the petition. You just had to kind of check off a box saying what kind of scientist you were. But most of the people who did this were actually not climate change scientists. They weren't scientists at all. So part of this information is true. Over 32,000 people did sign a petition. But, that's really not useful information because they're not scientists. And what's happened is that this kind of fake news has made it very difficult to talk and think about climate science because there's so much misinformation out there. And I want to talk a little bit about that misinformation. But this is real data here. This is real data. So I'm plotting the year, starting about 1998, going forward. This is the temperature difference. Okay, so this is not the actual temperature, it's just the temperature difference. What do you see? What do you see here? Is it going up? Is it going down? Yeah.
Well, it's slowly rising.
Um,
It's rising. It's all over the place, but it's really rising.
Okay. Okay, I might see a little bit of a rise there. Anybody else? This is real data. I'm going to draw a straight line through it. What do you think? It's kind of constant, wouldn't you say? I would. As a scientist, this is real data. It kind of bounces around a lot, and that's normal. That's normal that there's variability. And it's fairly constant. So from 1998 to about 2013, there wasn't a big change in the temperature data. So now there's a community of folks out there who are very interested in trying to convince us that there's no temperature change. And so they can take this data and show it to us. And in fact, it is true that there's very little temperature change over this relatively long period. I can add a few more data points. So this is 2014, 2013, 14, 15, and 16. And you see, now it's less true. Do you agree? But what's really important is put it into context. This is the entire data set. So what we've done, what I've done here is just show part of the data set. But this is the entire data set. And what do you see here? I mean, now this is pretty obvious, isn't it? It is certainly increasing. The period that we were, and then there's 2016. That's the last year. We're not done with 2017 yet, but I think it's pretty obvious here that it went up a little bit here, it's flat, and then it goes way up. So this is the real data. The other part here was also real data, but it's taken out of context. And when you take that data out of context, there's an element of truth to this, right? This is true. But it's a little like not telling the whole story. And it's important to tell the whole story here. I want to just point out, this is the data that I plotted here. And this is commonly done in the conversation about climate change. And it's one of the reasons we are confused collectively. And there's a reason why we're confused. There's a reason why folks are portraying that data there. So I'm going to give a couple more examples of, is this fake, that flat part that I saw? No, it's not fake. It's not a lie. It's true. But it doesn't reveal very much understanding. So there's knowledge that this is flat, but so that's something we know, but there's understanding that in fact, since we started taking temperatures, it's really out of context. So I want you to distinguish between knowledge and understanding, which is far deeper. And that's important to differentiate between just knowing something and understanding it. And I think you get what I mean when you're memorizing something the night before the exam. That's kind of knowing it, but you need to step back for a moment to try to understand it. Okay, so really what's happening here, and this is why so many climate scientists are concerned about it. All 16 years of the 21st century rank among the warmest years on record, and there's really no equivalent to this period of time in the temperature record that extends very, very far back. We've really never seen this before, and the climate science community is pretty freaked out. And we're very concerned, and that's one of the reasons I'm here today. So, I'm an academic and I study lots of things. I've got a year off, more or less, for my normal teaching, and this is what I'm thinking about. This is what I'm trying to do because I'm really concerned about it. And I think that, if you're paying attention, you might be concerned about it as well. So, one of my mentors, one of these really well-known climate scientists, his name is Dr. Lonnie Thompson. He studies ice sheets, and we'll go into that in a minute. But he was quoted as saying, any prudent person would agree that we don't yet understand the complexities with the climate system. Look at that for a minute. Read that. What does that mean? What's your take-home message from that? Any person would agree that we don't yet understand the complexities with the climate system. What would you do with that information? Yeah, what would you do with it? Sorry, I thought you were raising your hand. What would you do with it?
Where's the rest of the sentence?
Nice, yeah, okay, so somebody knew it. There's in fact, they cut this off, but if you heard Dr. Thompson say that, you'd think, we don't know much, we can't do anything. But actually what he said was, since we don't, we should be extremely cautious in how much we tweak the system. And tweaking the system means me driving to work, means you flying to Bermuda, means air conditioning this room. That's tweaking the system, is we're using a lot of fossil fuels. So this is happening frequently. Folks are taking our scientific words out of context. They're taking the data out of context, and they're taking the words out of context. And needless to say, that makes our job really difficult. Let's drill down at this temperature data a little bit more. I showed you kind of a two-dimensional way of looking at it, temperature versus time. And what I'm going to do now is show an animation of the entire planet. And we'll start off in 1880. That's kind of when we started getting good temperature records, and go forwards. And when we hit 1934, I want you to look at the United States, okay? And just don't forget 1934. And we're taking an average over 4 years. That's pretty common. So here we go. Blue is relatively cool. Here's the scale over here. Yellow is warm. Red is hot. And here we're 1934. Whoops, did you get it? I hope you did. But it's kind of bouncing around. And here we're in the 90s, 2000s, you're born more or less. And here's the 4-year period between 2012 and 2016. That's it. What do you get from that? What do you get? What sort of feedback do you get from seeing that? I know it's a big crowd. Just somebody raise their hand, please. What do you get? Yeah?
It's like 2 to 3 degrees temperature increase of the United States.
Yeah. But right, you were looking at the United States, there's a lot of temperature variation. One of the things that I get from that is how much variation there is over the planet. Right? There's a lot of variation over the planet. What we want to average it, because sometimes, the heat goes in some places and sometimes it goes in others. So there's a lot of variation, and yes, the United States did warm up over time. But this is a blog, this is a so-called climate science blog. They're looking at the temperature of the United States. Remember the temperature profile I showed you before it kind of went up? What do you see here? And if you're looking carefully, you can see that in that animation. 1934 is the warmest year in US. Just kind of ignore this for a minute, okay? If you don't mind. So now, you can use this fact. This is real data, and they've cheated a little bit. They've actually done a 60-month or a 5-year average. But this is true that 1934 was the warmest year in the United States. And what they say is that this is the warmest year on record. And do you see how they're taking real data and kind of playing with it, and playing with our interpretation of what's going on? And as a climate scientist, that bothers me a fair amount, because they say 1934 is the hottest year on record. They're using just the United States. So it is in the US, and notice they stop in 1990. They don't go on to the next 17 years, which are really important, because remember, this is what the record looks like. And this is the global average. 1934 is kind of lost there, because actually it's not the United States we worry about, it's the entire planet. I hope that makes sense to you. So this so-called climate science blog is really distorting the truth. They're using real data, they're using the real data, but they're manipulating it to make us think that actually it's not the warmest right now. And it's those kind of things that we need to have a better understanding, and we need to drill back. And it's hard. It's hard because it's hard to kind of know what kind of tricks they're playing on us. So the important thing to do here is look at averages over over several years, 10-year periods, and this is what it is. This 2016 is the hottest year on record. Year before was the second hottest. Year before that is the third hottest. And 2017 right now is about to surpass 2015 as the second hottest year. So we're breaking records, and this is not like breaking the track record or the swimming record for time. These are records we do not want to break. These are bad records to be breaking. So I want to try to understand what's going on here, right? What's causing this? At this point, there is very little conversation. There is no conversation in the scientific community about the fact that the temperature is rising. We got that. I mean, that's pretty, and actually there are very few skeptics who are disagreeing with it. Sometimes they're pulling 20-year data out of the hat, but generally there's an acceptance that the planet is warming. The question is what's causing it? And there's a theory that says that carbon dioxide is a heat-trapping gas. So if we increase the carbon dioxide concentration, the planet's going to warm. There's a theory that says that. And then if you plot, this is the CO2 concentration, and the blue and the red, that's temperature. What do you see here? We're after data. What do you see here? How does CO2 relate to temperature? What's that? Yeah. They look dead on, don't they? They look really, really close together, I would say. CO2 correlates well with temperature. This is a much longer record. So this is 300,000 years ago, 200,000 years ago, 100,000 years ago. The red is temperature and the blue is carbon dioxide. Is there a good correlation here? Yeah, this is pretty remarkable. When we got this data, we were like, wow, that's incredible. This is the smoking gun. And so the fact that there's such good correlation between this important greenhouse gas and temperature makes us, and the fact that there's a theory that suggests it's true, makes us think that That's right. I have a little animation here that should show up if all is good. Excellent. So now we've got different forces. This is the observed temperature, okay? This is that plot you just showed. And what we're going to try to do is match up various things and see what fits. Right? It's kind of like a jigsaw puzzle. See what fits in. Here we've got orbital changes. This is how the Earth revolves around the sun. Doesn't work. Would you agree? They don't look like each other. There are a couple of other things, natural causes, like volcanoes. The sun, obviously. The sun makes it warm, hot, cool, not. So solar changes. A lot of people were saying it's the sun. That doesn't look very good. Let's look at volcanoes. There is some variability back here, but generally volcanoes do make a difference, right? You see these big differences here, but they don't correlate well at all. So if you combine all these natural changes, these are all the natural changes. Doesn't look good to me. It really doesn't fit. You don't need to have a PhD in climate science to figure this out. So what else are we going to look at? Let's look at some things. This is land use. When we cut trees down, it matters. That's why we don't want to deforest the Amazon. And you see it does matter, but it's in the wrong direction. It's actually cooling the planet a little bit. What else could we think about? Ozone. Some people kind of confuse ozone and the greenhouse effect. It has a little bit of effect, but so far we're nowhere near the observed temperature record. Aerosols. These are these small little particles that really matter, but they are cooling the planet, not warming the planet. What's left? A little louder once. CO2 is left, right? Greenhouse gases, heat-trapping gases. Okay, here are the greenhouse gases. Looks pretty good, doesn't it? Doesn't quite match up, right? Why not? Because there are a bunch of different things that are in there, so we're going to combine them. Here is all the factors combined. Does it look good? Looks pretty good. So this is one way that we know that those greenhouse gases are an important contributor to the warming. Those aerosols cooled it, but this is one way. There are 9 other ways that we know that humans are the primary influence on climate change. Are you convinced? Yeah? Why is there so much doubt? Why is there doubt that humans are causing it? You know, I get folks coming by wanting to go to extra college, and they're like, are we certain? How do we know this? I see people constantly. Yeah?
Because it's this way, all this technology we have that's contributing to it, it's pretty much because the society without it would practically fall apart. People aren't really willing to try to fix that and rely on that create carbon dioxide similar and changing what the planet runs on.
Great, great. I'm going to interrupt you for a minute and pick one thing out there that you said, that people aren't willing to look at this carefully. And that's a really important point. This is, to me, what's most convincing. One of the things that's most convincing, in part, because this is what I study. I study this change here. We're going from a very cold period to a very warm period. It's relatively recent. That's kind of what I think and care a lot about. That's a relatively recent change. I mean, you know, it's not last year or even 100 years ago, but it's relatively recent for a geologist. And that rate of change is pretty fast. But this is what we're doing now, okay? This is 2007, and this is the CO2 concentration today. And that rate of change is much, much, much faster. And that's why it matters tremendously. There are natural changes, and we understand them well, but the natural changes change much more slowly than what we're doing here. And sometimes it's hard to kind of understand the data here. And so one way I like to think about it, it's like eating a big dinner. This rate of change is like eating a big dinner every day. And I don't mean just a regular dinner. I mean like turkey dinner over Thanksgiving. You know, you're just like, oh, that was great. 2 slices of pie, some ice cream, and at the end, you're really full. Now you can do that once every day, more or less. And that's what this rapid change is. But the rapid change that we're doing here is like having 6 of those turkey dinners in an hour. As opposed to 6 over the course of a week is 6 over the course of an hour. What's going to happen if you ate 6 huge turkey dinners in the space of an hour? Might throw up. And that's what we're doing now. That's a good analogy. It's not sustainable, and it's not gonna end well. We know that. And that's why, as a scientist, why I'm so concerned about it. I like turkey dinners, but I don't like how fast it's happening. I'm going to toggle through a few things here. We care a lot about ice melting. In fact, it's polar ice that's melting. Why do you care about polar ice melting? Somebody here. Yeah, why do we care about polar ice?
The level of the seas will...
Sea level's rising. Yep, that ice is melting, and it's going to cause some sea level change. This is the polar ice that's melting. This was 2007, 2012. And a lot of ice has melted. About half of the ice has gone away, and the thickness of the ice is also much less. And the real reason, another reason we care about it, is that ice is really shiny, and it reflects heat back into space. So the sunlight hits the ice, and it bounces off of it, and goes back into space. If that sea ice isn't there, the ocean absorbs the solar energy. So as the planet warms, the ice melts. There's less ice. There's more open water, which is basically black. That black open water absorbs a lot of energy, a lot of heat. It reflects back into space. Less heat is reflected back into space, and so the planet warms. You see what's happening? It's kind of like a snowball effect. You see that? And we're very worried about those kind of effects. That's the kind of thing that scientists worry a tremendous amount about. We call it a positive feedback loop. If you were eating an ice cream cone with a friend of yours and somebody said, oh yeah, there's this positive feedback loop, what would you think?
That's good.
That's good. Positive things, we like positive things. And that's part of the problem, is the way scientists communicate. We call this a positive feedback loop, but it's a really bad thing and we're scared about it. So we should use different words like vicious cycle. So that's part of the problem, is that the words that scientists use are confusing to most general people. And we got to get that straight. So we're going to call this a vicious cycle instead of a positive feedback loop. Okay, sea level's rising, right? Because of those glaciers, the ice sheets melting. And we're here. And this is the Tampa Bay here. I love it there. I don't usually swim in Tampa Bay. Probably you don't either. But what we're going to do is look a little bit at what's going to happen. This is a 3-foot sea level rise that's going to happen within your lifetime. And were you right about here somewhere? So you're not underwater yet. But if a hurricane came, and there's 5 feet of storm surge, this is what it looks like. That's without the sea level rise. Now I'm going to combine it with the sea level rise. That's not very good, right? And this is a good opening into when we present information that's really scary and bad and makes me want to do something, most people want to go back into their safe, secure zone. This sort of information that's scary turns out to be a really bad way of talking about climate change, because you think, oh, I can't do anything about that. That's really horrible. I'm going to have another ice cream cone, because you don't want to deal with it, right? I mean, somebody at Shorecrest should be dealing with this. Is anybody at Shorecrest dealing with this?
No.
Maybe, But you know, the fact is it's a long time from now, they think. So part of the problem is that this is really scary, and we don't like to hear scary things. I'm going to kind of go forward a little bit so we can move beyond it, because I really am interested in questions. What I toggled through was some pretty pictures of coral reefs, because we know that the carbon dioxide is going to go into the ocean. I'm an oceanographer, and cause the ocean to become more acidic. That makes us scared, and the corals are going to go away, and lots of ocean life is going to be affected. So that's another impact. And once we start kind of piling all these impacts onto it, it becomes pretty overwhelming. And a bunch of us just want to leave and worry about something else, like whether we can swim faster or bowl better or sail a different sailboat. You know, these things that we talk about are hard. But so I want to just kind of summarize what I think is important. If you were in the elevator with somebody like your uncle or your aunt or somebody who mattered, these are the 5 things that I think are important to get out of. It's happening now. You know that. You saw Irma. You saw the hurricanes hit Texas. You saw a whole bunch of effects. The sea level is rising now. We know that. And we're doing it. We're causing it. It's not natural causes. Those natural causes were a very small part of it. We're doing it. It's caused by humans. And what's really interesting that most folks don't know is that 97% of the folks, of the scientists who study climate scientists, agree that the temperature is rising. That's a no-brainer, right? And that we're causing it. So there's this tremendous agreement in the scientific community about the fact that the temperature is rising on the planet and we're causing it. And we really don't have a lot of time. If we wait 20 years or your lifetime or 10 years to do something about it, it's not soon enough. We need to act pretty quickly. The analogy I like to have is that we're hurtling down the interstate. Say your mom's driving. She's going a little fast. She's going 85 miles an hour, you know, on the interstate. And all of a sudden you see up ahead there's this accident. And you're going really quickly. And you know those accidents you see on YouTube. I watch them too. You know, they're kind of crazy, or from Russia or something like that. And all of a sudden there's this big accident. What do you do? What do you tell your mom to do? Slam on the brake! Mom, brake! And you're like this. You don't like sit and talk about it. You don't think about, what should we do? What should we do? You just slam on the brake. The airbags are going to go off in this scenario that I'm talking about. The airbags are going to get off. The question is it going to be a fender bender? Are we going to get driven to the hospital? Is the car going to get totaled? So that's what we're trying to figure out. How bad are things? But we can't wait. We really need to act soon. But the really good news is that we can fix it. This is not embedded. This is not necessarily going to happen. Some things are going to happen because we see them now. Some bad things are going to happen. There's no question about it. But I just put solar photovoltaic panels on my house. I'm living free. You know, I've got all that electricity generated. That's going to generate the electricity for my car. The U.S. has abundant clean energy. We've got lots of wind. We've got solar in the southeast and in Florida. And one of the things I told the governor, which is important for policy folks to care about and listen to, is that clean energy creates more jobs per energy than fossil fuels. So this is really a good thing. And business people can easily jump on board. So we can fix this problem. You know, the scientific community has pretty embraced the fact that this is our largest environmental problem. And it is controversial, and I think this is one of the important points to point out. Not because the science is controversial, it's not. When I go to my scientific meetings, when I'm having a cup of coffee with colleagues, we're not discussing this. This is obvious, but the conclusion is a bad conclusion, right? Because it might mean we're going to have to change things. or it does mean we're going to have to change things. So I'd like to encourage us to stop debating climate change, stop talking about these things that are just not true anymore, and start working to keep our planet and our people healthy. And one thing is enough to start off with. And one thing would be to replace, I don't know, is this an LED? Oh, these are halogens. We could replace this light bulb here. I think it's a halogen. We could replace that with an LED. They're cheap, they last forever. You know, that's one thing. So just doing one thing is a start. Biking, you know, I could ask you, invite you to think about, but just do just one thing. But I look forward to your questions. Thank you very much. Do it, do more. Okay, if we're losing ice really quickly, why don't we make an ice machine? So that's a really, that's a really good question. Because actually we're thinking about doing it, okay? So, no, I'm serious, not in the way that you might think. Because, do I have a picture of that? No, the Arctic and the Antarctic are too big. They're just too big. Like, make an ice machine, it would take a lot of energy to make the ice, and we use electricity to make the ice, and we use coal or oil to make the electricity, but too much ice. But there is a way that folks are thinking about, is putting up something that's like ice. It's a chemical that is very reflective, putting it up into the upper atmosphere so it reflects sunlight back into space. Pretty easy, right? Pretty good? Yeah, so there are propositions to change our climate, to alter our climate by putting up sulfuric acid aerosols in the upper atmosphere. The problem with that is that messing with our weather is, we haven't done that before. And it'd be kind of like, I don't know what you like to do, but it'd be like taking the engine out of your car. You don't really understand the engine very well. Taking it apart and trying to put it back together again. We don't understand the weather or the climate system well enough to be able to change it the way some people want to change it. But that whole geoengineering scheme is very tempting to try to do that. So interesting point, and people are talking about the geoengineering schemes. Yeah, in the back there.
Is the number 350 still what we need to retain the
Right.
CO2, or is it changed?
Right. Let's see. Well, this is good enough for context. So, the number was, is the number 350 still worth attaining? And the person who was the chief climate scientist in the government, Jim Hansen, wrote a paper a couple of years ago that said we need to get back to 350 parts per million CO2. So we're up here, and we're projected to go far higher. And he's saying that we need to be right about back here, 350. So we actually need to lower our CO2, and because in fact, you know, what appears to be about right is 300 or 280, so he's saying we need to go back to 350. It'd be nice. It'd be nice. But it'd be, you know, politically, I think it would be very, very, very difficult. And I think he said that because he thought it was true. But from a policy perspective, I don't think it is attainable. I think if we just try to, you know, basically keep it from going to keep it at 450 or 500, that's more realistic. 350 is not realistic. But, you know, the science shows that maybe that's what we should go for. Yeah, interesting point. One other question here. Yeah?
If we were able to begin fixing it tomorrow, how long would it take for the atmosphere to return to a...
Oh, fantastic question. Yeah, so this is where the science gets really interesting, right? So can you say your question again, please, and I'll repeat it?
If we began fixing things tomorrow, how long would it take for the carbon dioxide atmosphere to reduce to a
Right.
level?
So if we began fixing things tomorrow, how long would it take for the atmosphere to get back? Is that a good paraphrase of your question? It depends on what we did tomorrow. You know, So if we stopped all CO2 emissions, that's one approach. That's unlikely we're going to do it, but I'll answer your question as if we did that. So my buddy in graduate school, David Archer, actually answered that question about 10 years ago. It was really fascinating. And CO2 stays in the atmosphere for hundreds and thousands of years. And that's part of the challenge, is that when we hit the brake in this accident, we don't stop immediately, we skid for a while, right? I mean, I hope you have not been in an accident, but you've seen how cars skid. And there's a lot of momentum in the climate system. And so that momentum will keep us going for a while. Methane, which is another heat-trapping gas, has a much shorter time in the atmosphere. It goes away in like 20 or 30 or 40 years. So it's going to go away quickly, and that's good, because methane is really important greenhouse gas. But it takes a long time for the carbon dioxide to be removed from the atmosphere. So even if we stop tomorrow, we'd still have some problems for hundreds and thousands of years. That doesn't mean we shouldn't stop tomorrow, but it's part of the challenge. When we hit the brake, it doesn't solve it right away. One more question here, and then I'll move to the center. Was there a question here? Excellent, great. Okay, here, yeah. Yeah, great. So one of the ideas was to put more ice somewhere, and the other idea is to suck the carbon out of the atmosphere and put it somewhere. And this is a really great idea if we could do it well. So we've got carbon coming out of smokestacks that are burning coal or oil for electricity. And so if we could basically take that carbon dioxide and put it somewhere, then it wouldn't be in the atmosphere. And there are a bunch of different proposals, but basically we liquefy it. So CO2 is a liquid at very cold temperatures, like minus 60 degrees centigrade. So we liquefy it, and then we put it somewhere. Where do you want to put it? Well, the easy place to put it is in abandoned coal mines. So it's down there, we kind of put it down there, and then gradually over time it kind of leaks up. And so these abandoned coal mines are an easy, cheap place to put it, because we've already got a hole in the ground, and so we stuff it down there. But it might, so it might work for the short period of time, but over time it's going to kind of bubble up, and so that's not ideal. I'm going to flip the question back to you. Do you have another idea of where you put it? Nice. Put it somewhere cold. Well, I'm an oceanographer. It turns out if you put it at the bottom of the ocean, the CO2 is under high pressure, and those geeks among you, you know that high pressure and cold temperatures, the CO2 is going to stay a liquid. So there'll be literally a lake of CO2, and if we choose a place right, that lake will be where there's some sediments that are going to neutralize the CO2. Yay! The problem is it takes a lot of energy to liquefy the CO2 and pump it down to 3,000 meters or 9,000 feet, where these good sediments are. So it will about double or triple the cost of energy there, and that's a bit of a problem. So, but yeah, that may be what we do. And I kind of shortened the story. There are other ways of getting rid of the carbon in the atmosphere. But that's actually, I think that's a pretty good idea, mainly because I'm still driving around in my fossil-fueled car, and I want to visit my sister in New Mexico, and I don't want to ride my bike there, So, yeah, and China and India, they want like a refrigerator or a fan or maybe a car, right? They want those things, and that's really going to change the picture. Good question. And then go ahead.
What are the 3% of climate scientists say?
Oh, interesting. Yeah, so that study, by the way, has replicated it quite a bit. There are a very small minority of physical scientists who are concerned about the quality of the models. So that animation that I saw that kind of bumped up and down, that uses a model. So it's computer code that has all these interesting and important things into it. And they're much, much better than they used to be. And when that study was first done, they were kind of mediocre. and there was some criticism about the models. And then, I hate to portray it in such a negative light, there are a very small minority of scientists who are funded by the fossil fuel industry. And, so they get their money from folks who are paying them to get different results, the way tobacco companies funded research in the 60s and 70s that said that smoking wasn't hazardous to our health. Does anybody smoke on campus? I mean, you're not going to say that, right? No, we just don't smoke anymore. I don't know what's funny, but we just don't smoke anymore. It's just bad for our health. Okay, I got a question back there. Yes, thank you.
Because people tend to react when you go after the disease,
Right.
you go after it physically. What's your angle for talking to someone about climate change who is resistant, and with that in mind, how did the discussion with Governor Scott go?
Right. So the question was, if people react so negatively when we disagree, how do I talk to people who disagree with me, and how did my conversation go with Governor Rick Scott, who does not accept the science? First of all, it's hard. It's really hard, because as a scientist, I think, hey, information is where it's at. Just look at the data. But the fact is that if, let's say you and I disagreed about something, if we read the same newspaper article, we take different things out of it. So I need to embrace the fact that we take the information that we want to see. If I think my shirt is red, I'm going to continue seeing this as red. And it's hard to convince me otherwise. And so what I'm beginning to learn is that the really interesting stuff is coming out of the social science, not out of the climate or physical science. And so kind of the ice sheets melting, that's really interesting. There's a lot of new information on that. But basically, things haven't really changed in 10 or 15 years, aside from those ice sheets melting. I had a workshop on Saturday where we talked to, it was a role play, and we did not use the word climate change or sea level rise in our role plays. We tried to just use other language because as a way of just avoiding these trigger points. I think it's really unfortunate this has now become a partisan issue. And, we can blame Al Gore for that. He was trying to do the right thing. But now we've clearly divided things according to, if you're a Republican, you kind of got to deny the climate change. Except if you're in Florida. It's really cool. Our Republican legislators are like, they got it. Or they're getting it. Except for the governor. And so I think some folks are so beholden to financial interests. And let's back up for a minute. Let's think about these gas and oil companies. They've got hundreds. I don't know how much the coal and oil and gas is worth that they own. But imagine having a stash of marbles that are worth $10,000. And somebody all of a sudden wants your marble collection. I know you don't have a marble collection, but let's say all of a sudden somebody said, I want you to just get rid of those marbles. The marble economy is done. It makes sense that the coal and the oil and gas industry wants to hold on to their assets. That's what they're paid to do.
One more question, Brett.
Oh no, two more. I want one over here. Thanks. Yeah, so there is a concern about consumption, how much we are consuming, and then there's obviously something about population. And that's a tremendous concern. If we were just 1 million or 100 million people on the planet, it wouldn't really matter, and it didn't matter for millennia. And I think it's because that's not my field, to be honest. One question over here, and I want a student if possible. Is that okay? Unless. Okay. Is it you? Yes, it's you.
Dr. Brad, and I couldn't help but notice, other than the 17 years of obvious anomaly, but approximately every 100,000 years,
Yep.
rapid rise,
Yep.
carbon dioxide.
Yep. Yeah, that's what I do for a living, so I know the answer to that. That's Milankovitch cycle. This Croatian mathematician figured out how the Earth revolves around the sun and all the planets, and the way the northern hemisphere that has all those ice sheets It absorbs a lot of energy and reflects it back because those ice sheets are reflective. So we have a pretty good understanding. It's about astronomy and how the Earth revolves around the sun. And very small changes in insolation at the northern hemisphere at 65 degrees north in the summer affect the climate. Yeah, precession of liquidity, that sort of stuff. Yep. So we understand it, and that's kind of cool. Are we done? We are. Great.